Hello, my name is Eric, and today I'm going to be telling you about some work that I've done with my advisor, Mike Carbin, and this is how to program and reason with partial observability. So I think it's really interesting to consider what happens when we take our computer programs that we're writing and try to put them into real-world environments. And it's interesting because the real world is inherently partially observable. We can't know the exact state of the real world, but we get observations in the form of sensor inputs. And this creates a real challenge when these observations can be noisy or sometimes just completely wrong. And I think this is a domain where we don't have good abstractions to write programs. And what I mean by good abstractions are abstractions that allow us to reason about the correctness of the programs that we write. So let me give you an example. So say we want to build a drone, and this drone should be able to fly around and avoid collisions with the terrain. This is a problem because there is wind, and the wind can blow us into the terrain, and we don't know exactly what the wind is going to do. However, we can make observations in the form of an altitude sensor that tells us how high we're off the ground, and if we hit the terrain, that would correspond to 0 altitude. Unfortunately, this altitude sensor is going to have some inherent measurement error, and so just because it says we're at a positive altitude does not mean that we are safe from crashing into the ground. So how can we contend with this? Well, with a traditional programming methodology, what we would do is we would first write a state estimator that takes in our observations and produces a state estimate of how high we are off the ground. And we would use this to produce control actions. So if we're at about 400 feet, we might say that's too low, and so we need to increase by 50 feet. These control actions are passed back to the environment, and this continues on in a loop. Now, if we want to reason about whether this program is correct or not, one way or another we're going to need to build an environment model. And the environment model, you can think of it as a non-deterministic program that takes in control actions and produces observations, and it should capture the important aspects of the real-world environment. And now, to certify that this is correct, we can use your favorite verification technique, suitably adjusted for the non-determinism in the environment model. So what's wrong with this picture? So the problem is that there's a lot of cross-cutting concerns between the environment model and the state estimator. For example, if I want to increase the wind component that I allow to 30 miles per hour from 20 miles an hour, then the state estimator would have to change correspondingly. And furthermore, this is even more frustrating because if you think about what these things are doing, the state estimator is saying, okay, I got this observation, what environments could I be in? And the environment model is saying, okay, here is the possible environments you could be in, and here's the observations that you could get in each of them. So they're really doing the same thing. So in this work, we present a new programming methodology called belief programming. And here, the developer writes down the environment model, and we have a program runtime that executes the environment model to produce a belief state, which is the set of environments you could be in. We can then combine this belief state with observations from the real world to produce a state estimate. And just like before, we can then use the state estimate to produce control actions. Now, if we want to reason about the correctness of this overall program, we can do so in a self-contained way by assuming that observations came from the environment model. And then to certify that this program is correct, we've developed a new program logic called Epistemic Hoare Logic that enables us to reason about belief programs and their correctness. All right, so let's look at belief programming and Epistemic Hoare Logic in a little more detail and with respect to some code. So let's go back to the beginning and imagine how we would write some code to implement this drone example using the standard techniques that are available. So we're going to use this pedagogical language IMP, and this is a very simple language, but it will be sufficient for our purposes. So to start off, we're going to input an observation obs from the environment. We're then going to use a state estimator that is coarse-grained, so it says we're either too low, too high, or just right. And then using the state estimator, we're going to have control actions. So if we're too low, increase by 50. If we're too high, decrease by 50, and otherwise do nothing. So now, in order to reason about this program, we have to develop an environment model. So the environment model that we're going to be using consists of these 3 lines of code that I've written here. And at this point, I also want to add a correctness condition. The correctness condition is going to be in the form of a loop invariant. And what this loop invariant says is that the variable alt, which represents our true altitude, is between 450 and 550. So this tells us that we're 500 feet above the ground, plus or minus 50 feet. So that's a nice, safe altitude that ensures we won't crash into anything. All right, so let's look at how one iteration of this loop would execute. So we're going to assume we start off in a state that satisfies the correctness condition. So for example, alt equals 550 does. So the first thing we're going to do is we're going to execute this choose statement. And a choose statement is a non-deterministic choice primitive that takes in a predicate and specifies that the state of the program after executing the choose statement should satisfy the predicate, with the placeholder dot standing in for the value of the new variable that we're assigning to. So this choose statement says that the new value of altitude should be the previous altitude plus or minus 25. All right, so the next thing we have to do is produce our observation, obs, and we're going to do this the exact same way. We're going to say that obs is alt plus or minus 25. And now we're going to execute our state estimator. So in our example, obs is 572. So we're going to execute the to high branch because obs is greater than 525. And so this means our command is going to be descend by 50. And the environment model specifies that we're going to apply this command by adding it to the true altitude. So this is going to bring our true altitude back down to 515. And then I will now note that this true altitude of 515 satisfies our correctness condition. Okay, so what's the problem with this picture? So the problem with this program is that in the state estimator, we have these magic constants of 475 and 525. And so these are related to our correctness condition and our environment model, but it's not immediately clear from looking at this problem how we're related. But if we were to change our correctness condition or the environment model, these constants would be wrong. All right, so now I want to explain how we can make the transition to belief programming. So with a traditional program, the program state consists of an environment, which is a mapping from variables to values. And with belief programming, the core idea is that we're going to maintain a belief state, which is a set of environments. And the belief state is just the program state of the belief program. Okay, so let's look at how we could translate this program to use belief programming. So this code is in a new language that we developed called Blimp, which is a belief programming enabled version of Blimp. And it differs in the following ways. So we have a different correctness condition. We have this new type of statement called observation statements, and we have some different constructs in our state estimator. And one thing to notice is that the correctness condition and the state estimator use these modalities. And what these modalities mean is they're a way to build predicates on belief states. So the box modality means for every environment in the belief state, the inner predicate is true, and the diamond modality means there exists an environment in the belief state such that the inner predicate is true. Okay. Let's look at how this belief program executes. So again, we're going to assume we start off in a belief state that satisfies the correctness condition. So the correctness condition is 450 is less than alt and alt is less than 550. And so an example of a belief state that satisfies this just contains all the environments that have altitude between 450 and 550. It's worth noting that any subset of this belief state would also satisfy this correctness condition. Okay, so now we're going to execute the choose statement. And what a choose statement does on a belief state is for any environment in the belief state and any valid choice of the non-determinism, the resulting new environment should be in the new belief state. So this is going to have the effect of expanding the bounds of our belief state by 25 in either direction. And now we're going to execute the choose statement for obs, which is going to do something similar to the belief state, but on the obs variable, which I haven't depicted on the slide. Okay, and now we're going to make an observation. So we're going to take an observed value of obs from the real world, and in this case I'm going to use the example value of 572. And the update on the belief state is we're going to rule out all environments that are inconsistent with this observation. So we're going to rule out any environments that have obs not equal to 572, but because at this point the belief state contains only environments where alt and obs are closer than 25, we're also going to rule out any environments in the belief state that have alt as farther away than 25 from the observed value of 572. And so this is going to shrink our belief state like so. And now we're going to execute our state estimator. And so the state estimator uses these infer statements, which are like if statements, but they use these modal predicates. So which branch is going to execute? So let's look at the first condition. So it says, is it possible that alt is less than 450? And the answer is no, not according to our belief state. The second predicate says, is it possible that alt is greater than 550, or does there exist an environment such that alt is greater than 550? And the answer is yes, because in our belief state, we have an environment that has alt with 553. And so this predicate is going to get triggered, and we're going to execute the toHigh branch of our state estimator. And so we're going to get a command of -50. And when we add this to our alt, the meaning of this is to map over all environments in the belief state. And so this is going to shift our belief state down by 50. And now I will note that this new belief state also satisfies our correctness condition. And so this means we were correct on this execution of the belief program. So what have we gained? So if we look at the state estimator predicates for this belief program, they are much more intuitive to use than how we would write the state estimator previously using these magic constants. So if it's possible that the altitude is less than 450, then we're clearly going to break our correctness condition if we don't do anything. So we have to do something. So in this way, the ability to reason about the correctness of belief programs, it makes it much more intuitive to write programs using these abstractions. So now I want to explain how we can reason about belief programs using epistemic Hoare logic. And I want to do so by comparison to how we reason about classical programs using Hoare logic. So with Hoare logic, we have statements that look like this. We have a precondition, a program, and a postcondition. And the meaning is that if we start off in an environment that satisfies the precondition and execute the program, we should end up in an environment that satisfies the postcondition. Similarly, with epistemic Hoare logic, we have statements like these. And the meaning here is that if we start off in a belief state that satisfies the precondition and execute the belief program, we should end up in a belief state that satisfies the postcondition. And now our pre and post condition use these modalities to quantify over environments in the belief state. So what is this good for? So in the drone example, the key property that we need to show is that the loop body preserves its loop invariant, which is the correctness condition. So this means that if we start off in a belief state that satisfies the correctness condition and execute the loop body, we should end up in a belief state that also satisfies the correctness condition. How can we show this? Well, we should use the rules of epistemic Hoare logic. And there's a few too many for me to go over here in this talk, but if you want to know more about these, we can talk about them some more in the extended questions section that is going to follow. And these are in the paper too. Speaking of which, in the paper you can also find a semantics of BLIMP, which gives the fine-grained details of how belief programs work. You can also find the rules of epistemic Hoare logic and a soundness proof that the rules are sound with respect to the semantics. We also have a case study on the Mars Polar Lander. Mars Polar Lander is a lost space probe which is hypothesized to have crashed into the surface of Mars due to a control software error. We show in the paper that you can write the control software of the Mars Polar Lander using belief programming, and that you can verify using epistemic Hoare logic that such an error can't occur. Okay, so now I want to address some implementation concerns, with a particular focus on how do we represent these belief states. And you might be concerned about this because the belief state is a set of program environments, which is potentially a very large space, and it could potentially make our programs run very slowly. So we were concerned about this as well, so we went ahead and wrote an implementation. And we did the most basic thing we could think of, which is we implemented belief states using hash set data structures. And we used the drone example and the Mars Polar Lander as benchmarks, and for each of these we determined how fast does the belief program need to run in order to be feasible. And then we just ran these belief programs and saw how fast they ran. And what we determined is that initially the drone example was within its feasibility threshold, but the Mars Polar Lander was not. So we modified the Mars Polar Lander, particularly modifying the discretization window, and we found that with these modifications, the Mars Polar Lander was able to run within its feasibility threshold. And so these results are encouraging. Using the most basic implementation we could think of, with relatively little difficulty, we were able to get both these examples to run within the feasibility threshold. Another thing people wonder about is what is the relationship of this approach to other approaches, such as probabilistic approaches. And the answer is that probabilistic approaches are widely used, so there's a wide variety of related work to draw on. However, we found that for examples such as the Mars Polar Lander, which are amenable to a non-deterministic description of the uncertainty, a substantial reduction in the complexity of reasoning can be gained by using epistemic Hoare logic relative to the tools that you would need to use to reason probabilistically. All right, so to summarize, in this talk we talked about belief programming, and we talked about how you can use epistemic Hoare logic to reason about belief programs, And we looked at what does it take to make belief programming practical in certain domains. And I just want to say that if you're as excited about these things as I am, please get in touch with me. Come find me in one of the social channels or something. I'm more than happy to talk more about this, and I think there's a lot of interesting future work directions that we could take this in. So I'm happy to say more.